Hello everyone, today it's Dmitry Khizbullin with you here, and we are going to review the Huawei's DaVinci AI compute architecture. The presentation of DaVinci architecture was done by Heng Liao at Hot Chips conference a year ago. Definitely the technical details about DaVinci AI compute architecture are worth being reviewed even today. There is a wide variety of applications of AI in electronics, starting from smartwatches, moving further to mobile phones, then to autonomous vehicles, and finally arriving to huge data centers. Having the right scalable compute architecture is the key factor of success. Given the 6 orders of magnitude of performance range between the fields that you want to cover, you inevitably come to the dilemma of choosing between creating a specific architecture for every field, or choosing the unified architecture across the fields, which must be scalable enough to adjust to all the fields. And Huawei's team came with the latter. Based on DaVinci architecture, Huawei developed the range of cores starting from Tiny, ending with DaVinci Max core, which have not only architectural differences, but also vary with the range of cores incorporated into one chip. Huawei already has a wide variety of compute architectures in their portfolio, and mostly they differ with the trade-off between the performance, area or cost, and power consumption. The purpose of DaVinci compute architecture is to move this point in space to a more optimal location, specifically for neural networks and deep learning. Let's take a closer look into the details of implementation of DaVinci core. It has 3 types of compute units inside. The first is 1D scalar unit, which is standard for CPU cores. The second one is 2D vector unit, which is the one that helps to compute activations inside the neural network, for example. And the third, the most important type, is 3D matrix unit, which actually accelerates tensor computations, which are the core part of neural network computation. And you can see in the yellow highlighted row, if the side of a cube unit is 16 floating point numbers, then it is capable of computing for 1096 operations at the same time, simultaneously, thus speeding up the building blocks of neural networks, so matrix multiplications and convolutions. Huawei decided to go with the explicit memory hierarchy design, since it allows to gradually reduce the bandwidth when the traffic leaves the chip, On the diagram here, you can see the scalar unit, the vector unit, and the cube unit, along with the empty unit, which is a memory transfer controller. The different flavors of DaVinci Core have different parameters. So, for example, cube operations which are performed simultaneously may vary from 512 to 8192 operations. The range of operation performed by the vector unit also varies between architectures, being minimum for Tiny and maximum for DaVinci Max. The sizes of L1 and L2 buffers are also different. One thing that varies between the chips is if you take a look at DaVinci Max sub flavors, which are 310, 610, and 910. You can see that there is a different number of cores and different bandwidth, which corresponds to the core. So DaVinci 910 has 32 cores, and DaVinci 310 has 2 cores. All the design choices regarding the parameters of the cores were made, of course, as a result of thorough profiling of a variety of neural networks. So here on this slide you can see the profile of BERT, MobileNet, and ResNet 50. And what is actually plotted on the y-axis is the ratio of cycles consumed by the cube unit to the cycles consumed by the vector unit. So an important finding from here is that the most of the computation, especially in the deeper layers for computer vision networks, are spent in the cube unit. So of course the architecture is optimized for the maximal performance of the cube unit, and as a consequence the clock cycle spent on the vector unit can be effectively hidden by the time spent in the cube. In the same manner, to make sure that the bandwidth of memory doesn't become a bottleneck, other parameters like the width of L1 buffer bus is figured out. So from the profiling information you can see that the bus width of 2048 effectively is enough for execution of any of the benchmarked neural networks. Once the hardware architecture is done, it is time to design a software stack for the new DaVinci architecture. So at the very bottom level of the stack we have the low-level compiler. It's a C-like language with intrinsics, and it is very low level concept and language, which needs lots of expert knowledge about the architecture, and probably software developers would like to develop their operations on something more high level. So the more high level concept is TIC, and it is located approximately on the same level as CUDA and OpenCL. And even for the more hardware abstract high level development, there is TBE, which is an analog of TVM or XLA, which allows you to specify your computation, and then they will be automatically compiled down to the machine instructions. In DaVinci Core, we have several hardware units: cube unit, vector, scalar, and MTE, but they are not accessible at the same moment with sequential thread paradigm. So a single threaded paradigm cannot load them simultaneously. This can be a big problem for hardware resource utilization. To deal with it, there could be an approach of multi-threading, which allows several threads to interleave their utilization of hardware units. However, threads are quite expensive to manage in hardware. This means that there was a need to find a better approach, and a better approach is software multi-threading, which allows to interleave the operations in the source code, so that they are executed on different units. The height of the software stack needed to transform a neural network into binary code, which can be executed on the hardware, is very high, and there are many valid mappings from the high-level representation into the binary form. So DaVinci team has developed an advanced compiler which utilizes reinforcement learning to perform automated tiling of neural network operations. Putting all this together, we have a number of DaVinci cores, and moving upwards in the software stack, there is a task scheduler which assigns computation to the DaVinci core. Moving further up, there is a CAN layer, which is the architecture dependent component of the software stack, and above it lies a graph engine, which is architecture independent one, and on top of them there are several front ends, which a couple of them are familiar to the data scientists and machine learning specialists. They are TensorFlow, PyTorch, and at the moment Huawei develops Mindspore framework. It is open source, and it has the native integration with the remaining part of the software stack. Let's take a look at the range of SoCs which are designed using DaVinci AI Core. So the first one is mobile SoC, which is intended to be used in the mobile phones, and the most intensive computation happens in the NPU, in fact. So another area of application of neural network powered SoCs is automotive application, specifically ADAS, and here we can see the compliance with ASIL B and D levels intrinsic to the SoC, which is essential for automotive application. Huawei designed AI inference SoCs for edge and cloud inference, and of course the biggest in the series training SoC, Ascend 910, which incorporates 32 DaVinci AI cores, and is intended to be utilized in large-scale neural network training in the cloud. Let's figure out what's the memory wall and how we can deal with it. The core engine runs at very high throughput at the bandwidth. The memory bandwidth needed to saturate it is 2048 terabytes per second. Compared to HBM memory bandwidth of 1 terabyte per second, and HBM is the best throughput memory to date. We have the gap of approximately 2000 between the requirement for memory bandwidth and the compute execution. So to break this wall, Huawei creates a multi-level hierarchy of memory, which allows to reuse the data fetched into the level which is closer to the execution core. The old-style packaging of memory chips doesn't allow to break all the walls that it eventually faces. So Huawei developed 3D IC, 3D chip packing technology to increase bandwidth, reduce power dissipation. For the next generation of the design, HBM chips are actually put on top of each other and stacked vertically, forming a 3D structure, and this technique is applied not only for HBM chips but for SRAM chips, which are used as a cache. On this slide you can see quite sophisticated chip packaging technologies being evaluated for Huawei's mobile chips. Let's take a look what's the physical design of DaVinci chips. First, let's compare characteristics of Ascent 310 and Ascent 910. So the most notable here is Ascent 910, which has the peak compute horsepower of 256 teraflops of floating point 16 compute, and it also has hardware video decoders and the 128 of them, and the power dissipation for it is 350 watts. So it's a training neural network training chip, which is very, very competitive in terms of compute. How does Ascent 910 compare to the competitors, the class-leading devices from NVIDIA and Google? Here you can see that clearly in terms of teraflops of floating point 16 compute. Ascent is at least twice more powerful. This is due to all the architectural innovations which are incorporated into DaVinci architecture. Huawei puts 8 Ascent 910 chips into one AI server, so the total horsepower becomes 2 petaflops, and the total power consumption is 6,000 watts. Huawei also puts 2048 nodes together and form an Ascent 910 cluster, which delivers the peak performance of 512 petaflops. Amazing. It has hierarchical network structure connecting the nodes. Here is the shot of Ascent 910 die, which is quite complicated design, comprising of the compute core, Nimbus communication, and 4 HBM stacks on the sides. The total area is over 1200 square millimeters. On the floor plan of the main core, you can see the 32 DaVinci cores, and they are connected with the network on chip, organized as a mesh. For the inter-chip communications, there are 3 HCCS ports, and for inter-node communication, there are 2 100 gigabit per second RoC-E interfaces. The network on chip is organized as a mesh with 6 rows and 4 columns. So the bandwidth to on-chip L2 buffer is 4 terabytes per second, and the bandwidth to off-chip HBM is 1.2 terabytes per second. Here you can see the die shot of a smaller version, Ascent 310, intended for use in cloud and edge inference. And finally we can see some real photos of the manufactured chips. The presentation concludes with the slide highlighting future challenges, such as how to create a computer architecture for AutoML, which is supposed to be a more generic approach to designing the architecture of the neural network. What's the good computer architecture for reinforcement learning or graph neural networks? So how to design a software stack which is able to distribute the computation in the data parallel or model parallel or pipeline parallel manner. How to deal with the varying data precision. So different manufacturers prefer different floating point formats. Float 16, bfloat 16, TensorFloat. So these are the experimental floating point formats, which are deviation from my EEE standard. Thank you for staying with me for a review of Huawei's DaVinci compute architecture, and have a good day.